Hello and welcome to a projectile motion problem where we are shooting a cannonball into the air with the angle of 30 and the cannonball is the initial speed of 45 meters per second. So as you can see here, we're given the angle and the initial speed, and we are solving for the max height and how far that ball will be shot. So I'm going to solve A first, which is the max height, which this is also referred to as delta y, the change in y axis. So the first thing I like to do when I get this problem is draw it out. So we have a cannonball being shot. This is 30 degrees, and it is being shot out at 45 meters per second. It's going to be shot way over here and land eventually over here. So you kind of get the idea. And what we're solving for in A is that height. At the very top, or the apex, right here, I'll draw a line down, and this is going to be our delta y, or our height. So now I want to make an xy graph, because they do work independently of another, and I want to figure out exactly what we are given in each equation. So there we go, we'll plug that in eventually. But when we're solving for delta y, there's an equation that we want to use. And there are multiple, but the one I'm going to use for this is velocity y final squared equals velocity y initial squared minus 2g, g is gravity, delta y. There's our delta y, and that's what we're going to be solving for. The original equation is plus acceleration, but since our acceleration is negative 9.81. Thank you to gravity. It is negative g. So let's start plugging in what we need. The first one we need is velocity y final. Well, if you didn't notice, our velocity y final isn't given, sadly, and we got to solve for it. If you're wondering where that is, it's actually at the very end of this apex, right here. And our velocity y final up there is equal to 0. It has to be, because the ball is done moving kind of forward. It's now going to go on its decline, and if it weren't, then the ball would not be on the decline to its final position. So we know that that is 0. Velocity y initial isn't that easy. We have to solve for that one. In the equation, I will be doing it right over here on the right hand side of your screen, is velocity y initial equals velocity initial multiplied by sine of a theta. Velocity y initial is actually right here. I just didn't have enough room, so I wasn't going to do my work here. So velocity y initial equals. And then, as you know, velocity x initial is on the other side. So let's solve for it. Velocity y initial equals, our velocity initial is actually given, multiplied by sine of a theta. In this case, theta is 30. And you multiply those out, and you end up with velocity y initial is equal to 22.5. You can say meters per second, but I'll just leave it at that. So 22.5. There we go. So now we got to plug that in our xy chart. Velocity y initial equals 22.5, and we did solve for the velocity, we didn't solve for the velocity x, we solved for velocity y final, and we know that that is 0 in this case. So let's plug that in, equals 22.5 squared minus 2g is gravity, and that is the old 9.81, all multiplied by delta y. Thanks to that negative in front of the 2, we do not need to put negative 9.81. So 22.5 squared is 506.25. Subtract that by 19.62. Did that look a little cramped? All multiplied by delta y. And we are solving for this delta y over here, if you did not know. Let's make sure we write everything out. Alright, so now just simple, get that y alone, simple algebra. Subtract 506.25 out of there. 506.25 equals, it's an equals in there, I swear. Negative 506.25 equals negative 19.62 multiplied by delta y. Alright, one more step and we're almost there. Divide that by 19.62. Divide that by negative 19.62. The negatives will cross each other out, and then using your handy calculator, you'll end up with a number 25.8 equals delta y. You can add that little meters on there. So there we go. Let's go up here to the actual problem where it's written. Delta y equals 25.8 meters. Alright, there you go. You just solved for A. And now we've got to move on to the B and find that distance. Alright, now on to part B of the equation, which asks us how far will the ball land from the starting point. So we know that the starting point is right here, and our final is by that x. So we want to know, way down here, what this is, because it is the distance. From the starting point to the finishing point, that is the distance in between, or displacement. So that is known as delta x, because it is in the x-axis, x initial, and x final, which we'll be getting to right now. So I'll write right here, delta x equals, because that's what we're solving for. Delta x equals distance. Think of it like that. Okay, so the first thing I like to do is know what equation I'm going to use. So I'm going to look for an equation that involves the final and the initial. And the simplest one that I can think of, and there are multiple, is x final equals x initial added to velocity x initial multiplied by time. So let's write down what we know. X final, we don't know. That's what we're solving for. And x final, to explain that this actually works, if you look at x final equals x initial, if you subtract x initial, subtract it, x final minus x initial equals delta x, change in x. So there you go, little side equation to show you what we're doing. Let's see if this will erase. Alright, back to the problem. X final, now let's go down to x initial. This one actually isn't too hard. So here is x initial right here, and where are you starting? You are starting at 0. Can't really start anywhere else. Well, I guess you could, but in this situation, we're not. X initial equals 0. Plug that quickly into here. X initial equals 0. Great. Okay. Plus velocity x initial, which sadly is not given, so we gotta solve for it. Velocity x initial equals, well, the equation is velocity initial multiplied by cosine of a theta. And if that looks familiar, it should, because velocity y initial, which we just solved for, is vi multiplied by sine of theta. So you can kind of see how they're similar. So velocity x initial equals the initial velocity of 45, which is given, multiplied by cosine of 30. And then when you multiply that all together, you will get 38.971 equals velocity x initial. So let's plug that in up here. Velocity x initial equals 38.971. And plug that into our equation, bring it down, 38.971 multiplied by time. And time is not given, so we got to solve for that. And there are many equations for time, as I am sure you will know, but the one I'm going to be using is velocity y final equals velocity y initial minus gt. I know, we got to go back to solving for y stuff. There are other equations, but this one just made the most sense for this context. So the velocity y final actually has to do with velocity y initial. So if you remember from our other problem, velocity y initial equals 22.5. If you want to go and double check me, you can go back in the video and figure that out. but we know that 22.5 is equal to velocity initial. And if you're wondering, velocity initial, as I said earlier, is right here. So it would make sense that velocity final has got to be on the other side over here. Well, it is. It is actually going down. The opposite of velocity initial, it's going down. So velocity final, or velocity, I should say y of the final, to keep things the same. So obviously they have to somewhat correspond with one another. Well, they do. Since velocity y final is going down, it is in the negative direction. So all you have to do is just take that velocity y initial and add a negative to it. So ours is 22.5. So the velocity y final is that velocity y initial, just the negative, because instead of going up, we are now going down. So velocity y final is equal to 22.5, and don't forget that negative because we're in the negative direction. Alright, so now that we have that, we can bring that on over to our problem, which is right here. Velocity y final equals negative 22.5, subtracted by g, which we all know is 9.81 because it is gravity, and I talked about earlier why I'm not putting an extra negative there. Multiplied by time. You can see time is what we're going to now solve for. Subtract 22.5, subtract 22.5, and you will be given negative 45. Don't forget that negative, because we are subtracting them, the negatives do not go away. So negative 45, nice and easy, equals negative 9.81 multiplied by t. Alright, we're almost done. We're just doing the simple algebra of getting that t alone, because that is what we want. Divide each side by negative 9.81, and you will be given 4.587 equals t. Alright, so we can go and even plug that in up here. T equals 4.587. We can even add in velocity y final equals negative 22.5. There you see how they correlate with one another. So now let's go back to the equation. 38.971, which is velocity x initial, multiplied by our time, which we just found out is 4.587. Now, for your final step, you are going to be multiplying those together, and you will come up with the answer 178.8. I did round a lot of these numbers, so you may get something similar, but as long as you round 178.8, you should be correct. You can add that in. Our delta x is going to be 178.8. 178.8, because that is our x final. Subtract that by 0, which is our x initial, and you will get the same number. So there we go. We just solved for the height, which you will see on the other page, is 25.8 meters. And, of course, our delta x, how far did it land? 178.8 meters. There you go. That is how you do that.